How old are you? No. Wait, before you answer that, let me ask you something more interesting. How do you actually know how old you are? Most people would say something like, I was born in this year, it's now this year, so I subtract. Simple. Straightforward. Seems obvious. But think about it for a second. What did you really measure? What in the universe actually passed that allowed you to call it a year? What exactly are you counting? Because when you say you're 20 years old, or 30, or 50, you're not just stating a number. You're claiming that something has been ticking, consistently, reliably, ever since the moment you were born. But what is that thing? Is it the movement of the sun across the sky? The spinning of the earth? The beating of your heart? Or something even deeper, something built into the fabric of reality itself? Here's the strange part. We all feel like we understand time. We live by it. We schedule our lives around it. We celebrate it every year on our birthdays. And yet, very few people have ever stopped to ask what their age is actually measuring. Because your age is not just years. It's not just calendar pages flipping or clocks ticking on a wall. It's counting something far more precise, far more physical, and, in a way, far more mysterious than most people realize. And once you understand what that something really is, your idea of time, and even your idea of yourself, starts to shift. By the end of this video, you're going to understand what every clock in human history has actually been measuring. You're going to see what your age truly represents at the deepest level, and you'll realize that time is much stranger than it seems. So, before we go any further, we need to answer a very basic question. What does it actually mean to measure time? At its core, time measurement is surprisingly simple. A clock is just anything that repeats. That's it. If you have a process that happens over and over again, tick, 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 you can use each repetition as a unit. Count enough of those repetitions, and you've measured time. But here's the catch. Not everything that repeats is useful. For something to be a good clock, it doesn't just need to repeat, it needs to repeat consistently. Each cycle has to take the same amount of time as the one before it. No speeding up, no slowing down, no randomness. Just a steady, predictable rhythm. Because the moment your ticks become uneven, your measurement of time starts to drift. And once that happens, your clock stops being reliable. This leads us to an important problem. The world is full of things that repeat, but very few of them do it perfectly. Some processes speed up under certain conditions. Others slow down. Some are affected by temperature, motion, or even tiny changes in their environment. So while it's easy to find something that repeats, it's much harder to find something that repeats with absolute precision. And that challenge, the search for something that ticks the same way every single time, is what drove the entire history of timekeeping. Let's start with something simple, something you can feel right now. Your heartbeat. If you place your fingers on your wrist, you can feel it. A steady, rhythmic pulse. Thump, thump, thump. It repeats over and over again. Now imagine a world with no clocks, no watches, no phones, no calendars. Just people trying to measure time using what they have. You might say, meet me by the river after 1,000 heartbeats. In a rough sense, that could work. You count your beats, your friend counts theirs, and you both arrive at approximately the same time. So in this sense, your heartbeat is a clock. It repeats, and you can count those repetitions. But there's a problem. Your heart doesn't beat at a constant rate. Run for a few minutes, and it speeds up. Sit down and relax, and it slows down. Get nervous, excited, or scared, and it changes again. Even small things like breathing or thinking can subtly affect it. That means the length of one heartbeat isn't fixed. And if your basic unit of time keeps changing, then your measurement of time becomes unreliable. 1,000 heartbeats during a calm moment is not the same as 1,000 heartbeats after a sprint. So while the heartbeat repeats, it doesn't repeat consistently. And that leads us to an important realization. Not all repeating systems are useful clocks. If you want to measure time accurately, you need something more than repetition. You need stability. You need predictability. You need something that keeps ticking the same way, no matter what's happening around it. And that's exactly what humans started searching for next. Get smarter responses, upload files and images, and more. Log in. Sign up for free. If the human body wasn't reliable enough, the next step was obvious. Look beyond ourselves. Look at the sky. Long before mechanical clocks existed, Ancient civilizations turned to the most consistent pattern they could observe, the motion of the Sunday. Every day, the sun rises, moves across the sky, and sets. Then it rises again. This cycle repeats with remarkable regularity, so people began to define time based on it. One full cycle of the sun became a day. To divide that day into smaller parts, they used shadows. Place a stick in the ground, and as the sun moves, the shadow shifts position. Slowly, predictably, it sweeps across the ground. This was the birth of the sundial. Civilizations like the ancient Egyptians built entire systems around this idea, dividing daylight into segments what would eventually become our hours. For the first time, humans had a clock that didn't depend on the human body, but it still wasn't perfect. Sundials only work when the sun is visible. At night, they're useless. On cloudy days, they fail. And even more subtly, the length of a daylight hour changes throughout the year. Summer days are longer. Winter days are shorter. So while the sun is reliable in a broad sense, it's not consistent enough for precise measurement. That led to another idea. If the sky isn't always available, maybe we can build a clock ourselves. One of the earliest attempts was the water clock. The concept was simple. Take a container filled with water, make a small hole, and let the water drip out at a steady rate. As the water level drops, you mark the passage of time. It seems elegant, almost mechanical, and in many ways it was an improvement. Water clocks could work at night. They didn't depend on the weather. They gave people more control. But again, a hidden problem emerged. The flow of water isn't perfectly constant. When the container is full, the pressure is higher, and water flows faster. As the level drops, the pressure decreases, and the flow slows down. That means the ticks of this clock gradually change over time. Engineers tried to solve this. They designed more complex systems to regulate the flow, to keep the pressure steady. But these solutions made the clocks more complicated, more expensive, and still not perfectly accurate. So once again, we arrive at the same conclusion. These early clocks worked, but they weren't precise. They gave humans a sense of time, but not exact measurement. And that gap, the difference between roughly correct and perfectly consistent, would drive centuries of innovation. For a long time, this level of accuracy was enough. If you were a farmer, a trader, or a traveler, you didn't need perfect time. Around midday or later in the afternoon was good enough for daily life. But as societies grew more complex, that stopped being sufficient. People began to need precision. Take navigation, for example. If you're at sea, far from land, knowing your exact position becomes a matter of survival. Determining your longitude, your east-west position, depends critically on knowing the exact time. Even small errors in time can translate into huge errors in distance. Then there's science. As humans started studying motion, astronomy, and physics, rough estimates weren't enough anymore. To understand how the world works, you need measurements that are consistent and repeatable, down to very small intervals. And then there's coordination. As cities expanded and economies became more interconnected, people needed to synchronize their actions. Markets, transportation, labor, everything started to depend on people being in the right place at the exact right time, not just around the right time. Close enough was no longer acceptable. The world was becoming more precise, and timekeeping had to keep up. So the question became urgent. Is there something in nature that repeats not just regularly, but perfectly, something we can trust as a true measure of time? That search led to one of the most important breakthroughs in the history of science. The breakthrough came from an unexpected place. A young Italian thinker named Galileo Galilei was sitting inside a cathedral, watching a chandelier swing gently from the ceiling. It moved back and forth, again and again, tracing the same arc through the air. At first glance, there was nothing remarkable about it. But Galileo noticed something subtle, something most people would have ignored. He began timing the swings against his own pulse, and what he discovered was surprising. Whether the chandelier swung in a wide arc or a small one, each swing seemed to take almost exactly the same amount of time. That shouldn't be obvious. You might expect that a larger swing, covering more distance, would take longer. But it doesn't, at least not by much. When the swing is larger, it also moves faster, and these two effects nearly cancel each other out. This property is called isochronism, meaning equal time. It means that the motion repeats in a way that is nearly perfectly consistent. For the first time, there was a system that behaved like a true clock, and as Galileo studied this further, he uncovered something even deeper. The time it takes for a pendulum to complete one full swing depends on only a few things. It depends on the length of the pendulum, how long the string or rod is. It depends on gravity, the strength of the pull toward the earth. But it does not depend on the weight of the object at the end. A heavy metal ball and a light wooden one, if attached to strings of the same length, will swing in the same amount of time. And for small swings, it also does not depend on how far you pull it back. This was a powerful insight. It meant that timekeeping could be based on a physical system with predictable, stable behavior, something far more reliable than shadows, water, or heartbeats. For the first time, humans had found a way to build a clock that was grounded in the laws of nature themselves. Galileo understood the principle, but he never turned it into a working clock. That step came a few years later, through the work of Christian Huygens. In 1656, Huygens built the first practical pendulum clock, and the improvement in accuracy was dramatic. Before this, even the best clocks could be off by as much as 10 to 15 minutes per day. That level of error made true precision impossible. Huygens' pendulum clock reduced that error to about 10 to 15 seconds per day. That's not just an improvement, it's a transformation. Overnight, timekeeping became about 60 times more precise. And that change didn't just improve clocks, it changed how humans organize their lives. For the first time, people could rely on time down to the minute, and soon, even the second. Schedules became tighter, meetings became exact. Work could be coordinated with a level of precision that had never existed before. Navigation improved as well. Accurate timekeeping allowed sailors to determine their longitude more reliably, reducing the risks of long sea voyages. And as this precision spread, it helped lay the foundation for something much bigger: industrialization. Factories, transportation systems, and entire economies began to depend on synchronized time. Work shifts, production cycles, and logistics all required clocks that people could trust. In a very real sense, the pendulum clock didn't just measure time, it reshaped society. And perhaps the most important shift was this: time was no longer something vague or approximate. It became something you could measure, divide, and depend on down to the second. For all their success, pendulum clocks had an important weakness. They were still tied to the environment around them. A pendulum is not an isolated system. It is constantly interacting with the world. And that creates problems. First, gravity. The speed of a pendulum depends on the strength of gravity. But gravity is not perfectly uniform across Earth. It changes slightly depending on where you are. At the equator, Earth's rotation slightly reduces effective gravity. At the poles, gravity is a bit stronger. Even altitude makes a difference. That means a pendulum clock calibrated in one location will slowly drift if you move it somewhere else. Second, temperature. When temperature changes, the metal rod or string of the pendulum expands or contracts. Even tiny changes in length alter the swing period. On a hot day, the pendulum becomes slightly longer and swings more slowly. On a cold day, it shortens and speeds up. Over time, these small variations add up. Third, friction and air resistance. Every swing loses a little energy to the air and to the pivot point. Clockmakers had to constantly compensate for this, using escapement mechanisms that gently push the pendulum to keep it moving. But that introduces its own imperfections. Even with all the engineering improvements, the pendulum could never be completely isolated from its surroundings. And that is the key limitation. A pendulum is always dancing with the environment. Its timing is influenced by gravity, temperature, and local physical conditions, which means it can never be a truly universal clock. So even though pendulum clocks were a massive leap forward, they revealed a deeper truth. If we want perfect timekeeping, we need something that does not depend on where it is or what conditions it is in. We need a clock that is independent of the environment itself. Once the limits of pendulums became clear, a new idea began to emerge. If you want better timekeeping, you don't just need a better object. You need a faster one. At the heart of every clock is a simple principle: repetition. Each repetition is a tick, and each tick marks a step forward in time. But here's the key insight. The more ticks you can pack into a single second, the more precisely you can measure that second. Think about it. If a clock ticks once per second, your smallest measurable unit is 1 second. You can't really tell what happens in between. But if a clock ticks 1,000 times per second, suddenly you can measure time in thousandths of a second. You get much finer resolution. More ticks means more detail. More detail means higher precision. So the natural question becomes, how do we build something that oscillates faster and more consistently than a pendulum? This question pushed timekeeping away from large mechanical systems and towards smaller, faster vibrations, systems that could repeat thousands, or even millions, of times per second. Because as it turns out, speed isn't just about motion. In timekeeping, speed is precision. Once the limits of pendulums became clear, a new idea began to take shape. If you want better timekeeping, you don't just refine the same kind of clock. You change the scale entirely. Instead of building larger or more carefully balanced systems, you start asking a different question. What if the key to precision is not stability alone, but speed? At the core of every clock is the same simple principle: repetition. Each repetition is a tick, and each tick marks a step forward in time. But there's a deeper insight hidden in that simplicity. The more ticks you can fit into a single second, the more precisely you can divide that second. Think about it. If a clock ticks once per second, then your resolution is limited to whole seconds. Anything happening between ticks is invisible to that clock. But if a clock ticks 1,000 times per second, you suddenly gain access to millisecond-level detail. Time becomes far more finely sliced. Increase that further to millions of ticks per second, and you enter a world where time can be measured with extreme precision. So precision in timekeeping is not just about reducing errors in each tick. It's about increasing the number of opportunities you have to measure time. This leads to a crucial question that guided the next stage of clock development. How do we create systems that oscillate faster than anything mechanical like a pendulum, yet remain stable enough that their repetition is reliable? That question marks a shift in thinking. Timekeeping begins moving away from large, slow mechanical motion and towards small, fast vibrations, systems that can repeat thousands, millions, and eventually billions of times per second. Because in time measurement, something counterintuitive is true. The faster the rhythm, the more precisely time can be defined. Quartz crystals were a huge leap forward. They replaced slow mechanical motion with fast, stable vibrations, millions of oscillations per second, far beyond anything a pendulum could achieve. For everyday use, this was a revolution in precision. But even quartz has limits. A quartz crystal is still a physical object made of matter, and matter is never perfectly stable. First, temperature. When a quartz crystal heats up, its atoms vibrate more intensely. This slightly changes the shape and internal stresses of the crystal, which in turn shifts its resonant frequency. When it cools down, the frequency shifts again in the opposite direction. Even tiny temperature changes can cause measurable drift over time. Second, material imperfections. No crystal is perfectly pure or perfectly shaped. There are always microscopic defects, irregularities in the atomic structure, slight variations in density, internal stresses from manufacturing. These small imperfections subtly affect how the crystal vibrates. Over time, these effects accumulate. That means a quartz clock, even though extremely accurate, is not perfectly stable. It can drift by seconds over long periods, especially without compensation systems. Engineers try to reduce these errors using temperature control, careful design, and electronic correction circuits, and they succeed up to a point. But the deeper truth remains. No matter how refined the material, a quartz crystal is still tied to the physical world around it. It still responds to heat. It still carries imperfections. It still drifts. So even quartz, for all its precision, is not the final answer. It is a reminder of something important. If your clock depends on matter, it will always inherit the imperfections of matter. If quartz was the refinement of mechanical timekeeping, the next step was something far more fundamental. Instead of building a better vibrating object, scientists asked a deeper question. What if we use something that nature itself already keeps perfectly consistent? That idea led to atomic clocks. The breakthrough was realizing that atoms are not random, unstable systems. They are governed by quantum mechanics, and within that framework, their behavior is extremely precise. An atom can only exist in specific, fixed energy levels. It cannot have just any arbitrary energy, it must occupy one of these allowed states, like steps on a staircase rather than a smooth ramp. When an atom transitions between two energy levels, it absorbs or emits energy in the form of electromagnetic radiation. And crucially, this radiation has a very specific frequency, determined entirely by the difference between those energy levels. That frequency is not influenced by temperature in any significant way. It is not affected by pressure or the material conditions around it. It is determined by the fundamental constants of nature. This makes it an ideal reference for time. Among various atoms, cesium became the standard. In a cesium atom, there is a particular transition between two very close energy states in its ground configuration. When this transition occurs, it produces microwave radiation with an extremely precise frequency. That frequency became the definition of time itself. Today, the second is defined not by the sun, not by Earth's rotation, not by any mechanical device, but by the natural oscillation of cesium atoms. In formal terms, 1 second is defined as the time it takes for a cesium-133 atom to undergo exactly 9,192,631,770 oscillations of its radiation during a specific energy transition. This is a profound shift. Time is no longer something we approximate using physical objects that drift and degrade. Instead, time is anchored to a property of matter that is identical everywhere in the universe. Every cesium atom behaves the same way. A cesium atom on Earth is indistinguishable, in its relevant properties, from a cesium atom anywhere else in the cosmos. So when we define time using cesium, we are not inventing a human standard. We are discovering a natural one. And at this point, time measurement reaches a new level. A second is no longer just a segment of Earth's rotation or a mechanical tick. It is a precise count of atomic oscillations, something built into the structure of reality itself. What makes atomic clocks truly special is not just their accuracy, but their universality. Earlier clocks were always local. A sundial depended on Earth's rotation and sunlight. A pendulum depended on gravity and its exact length. A quartz crystal depended on its physical shape and temperature. Every step forward improved precision, but every step still tied time to the environment. Atomic clocks break that pattern. They rely on atoms, and atoms follow the same laws of physics everywhere in the universe. A cesium atom on Earth behaves exactly the same way as a cesium atom in deep space. Its energy levels are fixed by fundamental constants that do not change depending on location, temperature, within practical limits, or chemical environment. That means the tick of an atomic clock is not something that belongs to a particular place or object. It is something universal. To see why this matters, think about what a clock really is. A clock is a device that translates a physical process into a measurement of time. If that process changes, depending on where you are, your time measurement becomes local and unreliable. But atomic transitions do not depend on location in any meaningful way. They are governed by the same quantum rules everywhere. So an atomic clock built on Earth, in orbit, or even in interstellar space, would still define time in exactly the same way. There is another subtle but deeper point. With atomic clocks, time is no longer something we infer indirectly from messy physical systems like moving shadows or swinging weights. Instead, time is directly tied to the behavior of fundamental particles. This shifts the meaning of time itself. Time is no longer just a human convention or a practical tool for organizing events. It becomes something embedded in the structure of physical law. In this sense, time stops being just a background in which physics happens. It becomes part of physics itself, a measurable property of the universe, defined by the most fundamental and universal processes we know. At this point, something surprising begins to emerge from all this precision. We've gone from heartbeats to sundials, from water clocks to pendulums, from quartz crystals to atoms. With each step, we found a more stable and universal way to measure time. It almost feels like we are getting closer and closer to one perfect, absolute time. But then comes a major realization, one that completely changes the picture. Enter Albert Einstein. Einstein showed that time is not what we instinctively think it is. It is not universal. There is no single shared now that the entire universe agrees on. There is no master clock ticking at the same rate everywhere. Instead, time depends on motion and gravity. First, speed. If you move very fast compared to someone else, your time does not pass at the same rate as theirs. From their perspective, your clocks run slower. From your perspective, theirs run slower. This is not an illusion or measurement error, it is a real physical effect. Second, gravity. The stronger the gravitational field you are in, the more slowly time passes for you, compared to someone in a weaker gravitational field. Clocks closer to massive objects tick more slowly than clocks far away. This means time is not fixed. It stretches and compresses depending on how you move through space and how deep you are in gravity. And this leads to a profound shift in understanding. Even if you use the most perfect atomic clock in the universe, it will still measure a time that depends on its path through space-time. So, instead of one universal time flowing identically everywhere, we get many times each one valid, each one real, each one tied to a specific observer and their journey through the universe. This is where time stops feeling intuitive. Einstein showed that time is not fixed, it depends on how you move and where you are. First, the effect of speed. Imagine two twins. One stays on Earth, while the other travels in a spaceship moving extremely fast close to the speed of light. The traveling twin eventually turns around and comes back. When they reunite, something strange happens. They are no longer the same age. The twin who traveled at high speed has aged less. Their internal clock, everything from heartbeats to chemical reactions to atomic vibrations, has run slower compared to the twin who stayed on Earth. This is not science fiction. It is a real prediction of physics called time dilation, and it has been experimentally confirmed. Now comes the second effect, gravity. Time is also affected by how strong gravity is. If you place one clock at sea level and another on a mountain, the clock on the mountain will tick slightly faster. Why? Because it is farther from Earth's mass, and the gravitational field is weaker. Closer to a massive object, time slows down. Farther away, time speeds up. So gravity bends not only space, but time itself. Put these two effects together, and the result is striking. Two people can experience different amounts of time passing, even between the same two events. They can age differently, simply because they took different paths through space and time. One traveled faster, one stayed in stronger gravity, one experienced less time overall, and both are correct within their own paths. There is no single shared clock making a universal judgment. Time is not identical for everyone, it depends on motion and gravity, and therefore depends on your journey through the universe. This might sound like a theoretical idea at first, something that lives only in equations and thought experiments. But in reality, it has been tested, measured, and used in everyday technology. One of the most famous tests was done using atomic clocks on airplanes. Scientists took extremely precise atomic clocks and flew them around the world on commercial flights. At the same time, identical clocks were left on the ground as a reference. When the clocks were brought back together and compared, they did not match. The differences were tiny, measured in nanoseconds, but they were real. The moving clocks had experienced time slightly differently because of their speed and their altitude. This matched exactly what Einstein's theory predicted. This experiment showed something important. Time dilation is not just a theory. It is a measurable physical effect. But perhaps the most practical and surprising application is something you use every day without thinking about it. GPS. Global Positioning System satellites orbit Earth at high speed and at high altitude. Both of these conditions affect time. Their speed makes their clocks tick slightly slower. Their weaker gravitational environment makes them tick faster. The combined effect is a small but constant difference compared to clocks on Earth's surface. If this were ignored, GPS calculations would quickly become inaccurate. In fact, position errors would grow by kilometers every day. So engineers must correct for relativity. The satellite clocks are adjusted so that when these effects occur in orbit, everything stays perfectly synchronized with Earth-based time. This means every time you use navigation on your phone, whether you're finding a location, booking a ride, or tracking a delivery, you are indirectly relying on Einstein's understanding of time. Relativity is not just abstract physics. It is built into the infrastructure of modern life, and it confirms something profound. Time is not absolute. It is physical. It is flexible, and it depends on motion, gravity, and the path you take through space-time. Now we can return to the question we started with. How old are you really? At first, it seems like a simple answer. You count the years since your birth, based on calendars and dates. That's how we usually define age. But after everything we've explored, that definition starts to look more like a convenient approximation than a fundamental truth. Because calendars are not nature, they are conventions. They rely on Earth's motion, which is not perfectly constant. And more importantly, they assume time flows the same for everyone, everywhere. But Einstein showed us that this isn't true. So your age cannot simply be years on a calendar. It cannot be tied to something as imperfect as Earth's rotation or human agreement. Instead, we have to define it more deeply. Your age is the amount of physical time your body has actually experienced along its journey through space-time. And at the most fundamental level, that means something very specific. Your age is the total number of atomic oscillations that have occurred in your body since the moment you were born. Every cesium-like transition, every vibration of atoms, every consistent physical process that acts like a clock, all of it contributes to your personal measurement of time. This is what physicists call proper time, the time measured along your unique path through the universe. And here is the key insight. That number is not identical for everyone. Two people born at the same moment can end up with slightly different ages if they experience different conditions, if one moves faster, or spends time in stronger or weaker gravity. The difference is usually tiny in everyday life. You would never notice it in normal circumstances. But it is real, measurable, and fundamentally built into the laws of physics. So when you say, I am 30 years old, what you are really doing is summarizing an incredibly complex physical history, your entire journey through space-time, into a single, human-friendly number. Not just years, not just dates, but the accumulated ticking of physical reality along your life. Once you accept this, something even deeper changes in how you think about time itself. If time depends on motion and gravity, then the idea of a single universal clock, one shared timeline that the entire universe follows, starts to fall apart. There is no master clock ticking somewhere in the background of reality. There is no single now that is the same for everyone. Two observers, moving differently or sitting in different gravitational fields, will not agree perfectly on what is happening right now in distant parts of the universe. Their slices of time don't line up in a universal way. This means the present moment is not a global event shared by everything that exists. It is local. It belongs to each observer individually, and so a new picture emerges. Instead of one universal river of time carrying everything forward at the same rate, reality is more like a vast landscape where every observer has their own path through space-time. Each path has its own measurement of time, its own sequence of events, its own accumulation of change. In that sense, each person carries their own time with them. Your time is not identical to mine in a perfectly strict sense. They are extremely close in everyday life, but fundamentally, they are not the same object. This is one of the most profound shifts in physics. We go from thinking of time as something external that the universe shares, to something internal that each observer experiences along their own journey. Time is no longer a single background stage. It is part of the path itself. Once you reach this point, the question stops being just about clocks or measurements and becomes something much deeper. What is time, really? Physics gives us an incredibly precise way to measure it. We can define it using atoms, calculate how it changes with speed and gravity, and predict its behavior with extraordinary accuracy. But none of that fully answers the bigger question, why does time exist at all? One possibility is that time is fundamental. In this view, time is a basic ingredient of reality, something that cannot be broken down further. It is part of the foundation of the universe, like space, energy, or the laws of physics themselves. Things happen in time, and time is simply the arena in which change occurs. But there is another possibility. Maybe time is not fundamental at all. Maybe it is emergent. In this view, time is not something the universe has at the deepest level. Instead, it is something that appears when you look at large collections of interacting systems like atoms, particles, and fields. Just as temperature emerges from the motion of molecules, time might emerge from deeper underlying relationships in physics. In that case, time would not be a fundamental thread running through reality, but a kind of large-scale pattern that appears when complexity builds up. And then there is another layer to consider. perception. Even if time exists as a physical quantity, our experience of it may not reflect it directly. The feeling that time flows, that moments move from past to present to future, could be something constructed by the brain as it processes change, memory, and prediction. From this perspective, time might be part physics and part perception, something that exists in the universe, but also something shaped by how conscious systems interpret change. The truth is, we don't yet have a final answer. We can measure time with extreme precision. We can describe how it behaves under almost any condition we can test. But when it comes to its deepest nature, time still remains one of the open questions in physics and philosophy. And that is what makes it so fascinating. The story of timekeeping doesn't end with atomic clocks. In fact, we may only be at the beginning of what's possible. The next generation of clocks is already being built, optical atomic clocks. Instead of using microwave transitions like cesium, these clocks use transitions in atoms that oscillate at much higher frequencies in the visible or near-visible part of the electromagnetic spectrum. These frequencies are hundreds of trillions of cycles per second. And here's the key idea. Higher frequency means finer resolution. Just like moving from pendulums to quartz increased precision, and quartz to atomic clocks increased it again, optical clocks push that precision even further. They can measure time so accurately that even tiny effects previously invisible start to become measurable. At this level of precision, timekeeping stops being just about telling time. It becomes a tool for probing the universe itself. One possibility is detecting gravitational waves in new ways. Gravitational waves are ripples in space-time, caused by massive cosmic events like colliding black holes. They were predicted by Einstein and only directly observed in recent years. But optical clocks could one day become sensitive enough to detect even subtler distortions in space-time, opening a new way to listen to the universe. Another possibility is testing whether the constants of nature are truly constant. We assume quantities like the fine structure constant, something that governs how strongly light interacts with matter, never change. But with ultra-precise clocks, we can compare atomic transitions over time and across space to see if these values remain perfectly stable. Even a tiny drift would revolutionize physics. And then there's the deepest and most speculative idea of all, the structure of space-time itself. Some theories suggest that at extremely small scales, space-time might not be smooth and continuous, but instead have a kind of grainy or discrete structure, often called quantum foam. If that's true, it might leave subtle signatures in how clocks behave at extreme precision. None of this is confirmed. These are open frontiers. But there is a pattern here that history keeps repeating. Every time we build a better clock, we don't just measure time more accurately, we discover something new about reality. Better clocks revealed irregularities in Earth's rotation. Better clocks made GPS possible. Better clocks confirmed relativity. And future clocks may reveal things we don't yet have words for. Because when you measure time more precisely, you are not just tracking change. You are probing the deepest structure of change itself. We started with something very simple. Shadows moving across the ground. Heartbeats pulsing in the chest. Early attempts to make sense of change using whatever nature gave us. From there, we built better and better ways to measure time. Sundials gave structure to the day. Water clocks brought measurement into the night. Pendulums introduced regularity. Quartz brought precision. And finally, atoms gave us something universal, something rooted in the deepest laws of physics. Step by step, our understanding sharpened. And now we can say something remarkable. Time is no longer just what we guessed from the world around us. It is something we can define with extraordinary precision using the behavior of atoms, the same atoms that exist everywhere in the universe. But if you follow this all the way through, it leads back to you. Your life, your experiences, your growth, all of it is happening along a path through space-time. And along that path, countless physical processes are unfolding. Atomic vibrations, chemical reactions, biological cycles, all of them acting as clocks. So when we say your age, we are not just referring to a number on a calendar, we are referring to a physical record of everything that has happened to you since you were born. A count of time measured not by human convention, but by the universe itself. Your age is, quite literally, the accumulated history of your journey through space-time, written in the ticking of physical reality. Now imagine this. You take a perfectly accurate atomic clock and send it on a journey. It travels near a black hole close enough that gravity becomes extremely strong, but not so close that it falls in. It orbits there for what feels like a short time to the clock itself, maybe 1 hour, maybe 1 day, then it returns to Earth. When you compare it with an identical clock that stayed here, something strange happens. They no longer agree. The clock that stayed near the black hole has experienced far less time. While it ticked through a small number of cycles, the clock on Earth may have advanced through days, years, or even decades. From our perspective, the clock near the black hole was running slow. From the clock's perspective, nothing felt unusual at all. This is not imagination. It is a direct consequence of gravity shaping time itself. So the question becomes, if you could send a clock on such a journey deep into extreme gravity, around a black hole, and back, how much time do you think would pass for each observer? Would it be minutes versus years? Days versus centuries? Something even more extreme? There is no intuitive answer, because our everyday experience never takes us anywhere near these conditions. But physics tells us the effect is real, and it can become dramatic. Now I want to hear your thoughts. If you could send a clock near a black hole and bring it back, what do you think it would reveal about time? Write your answer in the comments.